Okay, all right. Yeah, so it's just another one of those times where I decide that it's a good idea to do a presentation with 2 days' notice. It always gets the blood pumping. I guess you guys thought you were out of audience participation now that now that we've finished the introduction. But you're wrong, because I have a game for us all to play. So I'm thinking of a number between 1 and 100. Anyone want to guess what it is? 22? Let's see. No. 25? Is it 25? 42, let's see. No. Sorry? 45. Draw any square. No. 1. It's not 1. 78. No. 100. No. Well, 96. Is it 96? No. See, as you can tell, this is going to take forever. And that's because there are 100 numbers and only one of them is actually right. But you could think outside the box and ask some different questions. For example, is it greater than 50? In this case, it is. Or is it even? It isn't. Is the ones digit greater than 5? No. And you can draw any kind of these patterns on top of this grid. And ask all different questions and eliminate a whole bunch of things at once. But the really cool thing is, and you can do this in any order, but if you ask all these questions at once, then you can really quickly narrow it down. And like this can happen in just 7 questions, which is log to 100. But there's an interesting thing here too, whereas like if I would have asked, I'm thinking of 50 numbers between 1 and 100, this wouldn't have worked, right? Because you can't narrow down on 50 numbers. Anyway, nice little thing to think about. Let's get on with the talk. Yes, so I think you should know about compressive sensing. So who am I? I'm Alex Tritt. That's me in the lab. I'm in the lab because I'm an experimental physics PhD student at Monash. And so I work in quantum sensing, which is part of quantum technology. And I'm supervised by Lincoln Turner, who's a physicist, and James Saunderson, who's an applied mathematician. James does more stuff around machine learning and that, but the fundamental math side of things. And so I use this thing in my work called compressive sensing. And I talked to a bunch of you guys about it the past few times I've been here. And it seems people don't really know what it is. And I think you guys will be interested. We'll see. But yeah. So I won't go into all the quantum stuff too much. So sorry for any of you who have heard of it, because you're about to be physics-explained to. But yeah. But I guess, so I do know machine learning proper from a course 4 years ago, but I know that's quite out of date. Anyway. So I think the difference between, so I consider compressive sensing like machine learning adjacent. And I think the difference is that with data science and machine learning, you're looking at these mathematical techniques to process data you already have. But with compressive sensing, we're using these same kind of techniques to get the data in the first place. So one of the big questions in getting data is how many measurements do you actually need? And this has been answered a long time ago in the Nyquist-Shannon sampling theorem. So if you have a signal and it lasts for a finite amount of time and it has a finite bandwidth, maybe it's looping or something to make that possible, then you can sample it in a finite number of samples. But that finite number of samples still might be really big. And this could be a problem because data taking can be expensive. Maybe not for taking pictures or something like that. But maybe if you're taking a picture in a weird wavelength, like infrared or ultraviolet, maybe the photosensor is literally expensive to make. But the expense could be figurative as well. For example, if you're me and you've had cancer recently, then you might need CT scans, which can give you more cancer. So as fewer measurements as possible is good. Or you could be like me, who has Crohn's and needs MRI scans of the gut, and MRIs are just uncomfortable. Or you could be like me, who does work with quantum materials and they're super fragile. But yeah, even if you're not me, there are still applications too. So we really want to get away from this fundamental limit of the Nyquist theorem. And so we already know somewhat how to do that with compression. And I guess the thing to know here is that pretty much all useful signals, like we don't want to just look at white noise. We're looking at things with structure, and if things have structure, then they're sparse in some sense. So if you have this lovely picture of me, then the picture has a bunch of blocks of color. It's not just white noise, which means it has a very sparse frequency transform, and that just means a lot of these DCT values are black here. So so there's 0. And this is like 90% of how JPEG works. There's more to it, but anyway. But the problem is you still have to take the full picture to then analyze it and then do the compression. So you still have to take all those potentially expensive measurements. So we're kind of back to the drawing board. So now, because I'm a physicist, I'm going to bring in the Heisenberg uncertainty principle. But what I mean by that here is that signals with condensed energy in like a time domain have spread out energy in a frequency domain. So say if we have this nice little pulse, if we take a Fourier transform, it turns into a nice little sine wave, but the sine wave is spread out across the whole frequency domain. So if you are measuring in this time domain, if you just pick a random time to measure, then chances are you're going to measure very little information. But if you're measuring this frequency basis, then it doesn't matter where you measure, you'll get something interesting. This is true for sparse signals in general. And so this is kind of like the game at the start. So when we ask sweeping questions like is the number greater than 50, where we ask about like the whole range of values, that's kind of like here where we're asking about like a particular frequency. So it's kind of like that. And you could even see on the grid, actually, they kind of look like blocky frequency transforms, like blocky waves as well. And just like at the start, we can get away with recovering a full signal with way fewer measurements than the Nyquist theorem would suggest we would need. And so this is the key to compressive sensing. It's also called compressed sensing or compressive sampling, or conveniently CS, which is nice. And basically, this came about because the best mathematicians in the world, this is like Terence Tao worked on this, all got together and they came up with a nice formal theory about how to best win a game of Guess Who, because of course they did. And I guess, so the measurement itself is the compressed form. So whereas with JPEG, you have to take the measurement and then compress it. So how do we recover the signal from a subsample of measurements? So because we have a subsample of measurements, there are actually lots of signals that could fit the data that we take. But because the ground truth signal is sparse, we can assume that the correct recovery will be the sparsest signal that fits the data. So here's an example where this is real data I took in my quantum stuff, but all of these are signals that fit the data, which is this y value here, but we're only interested in this very sparse one in the middle. And when I say sparsest, est means we're looking at an optimization problem. So we use the optimization problem to recover the signal. So when does it work? So because we are taking like an incomplete set of measurements, we actually have a choice of, say, which frequencies we want to measure. So the important thing is for the set of frequencies to have no structure. And so you can't just take every second frequency or just the lower frequencies. But on the other hand, if you just select frequencies randomly, that is very likely to have no structure to it. So you can just do that. And there's a bit more to it in this very dense textbook. As for the optimization itself, so optimizing for sparsity is an NP-hard problem, so that's not good. But compressive sensing theory figured out that you can actually relax this requirement to minimize this L1 norm here. And one way to do that is with the lasso problem, which you've probably seen in other machine learning applications. And so here are what the norms mean for reference. And basically, like, because this is just like a loss function. So this is just saying, I'm going to punish you for giving you more loss for not fitting data. And this one's just saying, I'm going to punish you for not being sparse. And when I was timing myself, I didn't really have time to go into why, but it's to do with if this line represents all signals that fit the data, the point where it crosses this axis is the sparsest point, because then x1 is 0, because that's what sparsity means, where you have the most zeros in the signal. And this also happens to be the same point which intersects with the smallest possible diamond, which is representative of this L1 norm here. So that's kind of why. Yes. Right, so let's see an example then. So this is just something I coded up in like 20 minutes, because why not? So you can't do gradient descent on the lasso, but you can do the next best thing, which is called ISTA. It's pretty much the same, but you have to be careful because of the spiky diamond, basically. Yes, and so here's the example. We have this lovely picture of me again. And let's only sample 20% of the pixels. And so all of those green pixels, we're going to say the computer has forgotten about. Here's a close-up, so you can see there are some left. And what we want to do is 100 iterations of this basically gradient descent to get the signal that best fits this sampled data with the sparsest spatial frequency transform, so like the DCT we saw before. And so after we do that, we get this thing. And it's not perfect, but yeah, I think it's all right for something I coded in 20 minutes. And yeah, so it emulates an actual device called a single pixel camera, which solves the problem of those frequencies, like the wavelengths of light that are hard to measure from before, but I also figured out I don't really have time to go into that. And yeah, I put the code on GitHub, so you can play around with it, because why not? Yeah, so to wrap it up, recommended reading. This is like a good introduction, and this one is like very dense maths, but it actually tells you all you need to know. So how is this relevant to my work, just quickly? So in our lab, we make the coldest material in the universe, and it's called a BEC. And this is it in the process of being cooled down. It's this purple blob in the middle of a vacuum chamber surrounded by coils. It's not actually purple, it's glowing in infrared, but that goes through the phone camera. so you can actually take a picture of it. But this is actually a much cooler picture in both senses of the word, because I'm guessing you've heard of Schrodinger's cat, where the cat is both dead and alive at the same time. So all of the atoms in this picture are in all three clouds at the same time, right before we take the picture. So I think that's pretty cool. Yeah, so I guess BECs are, yeah, I mean, I didn't script this, but I really like BECs because it's quantum mechanics on like a macroscopic level, so you can actually see it. I probably wouldn't believe quantum mechanics if I didn't see this all the time, because it's quite wacky. But anyway, so the BEC is sensitive to magnetic fields, and so we're trying to use it as a very sensitive magnetic field sensor. And because it's hard to control and fragile and stuff, that's why we want to use compressive sensing with it. So we can get as much out of our measurements as possible. And so just to wrap things up, so compressive sensing is really about asking useful questions and doing useful measurements. So no matter how good the measurements are, you won't be optimal unless you ask the right questions. And this is, of course, a deep mind from Hitchhiker's Guide, who famously answered a bad question. And yeah, but anyway, so this is your chance now. Any questions?
What does BEC stand for?
BEC stands for Bose-Einstein condensate. So it's another phase of matter, just like solid, liquid, gas, and plasma. Yep.
The algorithm used for JPEGs, I don't understand when you're using photographing the BEC field as well. The one that's 90% of the JPEG compression. Are you using the same algorithm for the BEC images?
Pretty much. I'm not, so, yeah, so kind of. So the algorithm ISTA has a fast version called FISTA, and I'm using FISTA for the BEC stuff. We're also not taking pictures of the BEC. We're trying to look at its behavior over time. So we're actually looking at a time domain signal. But yeah, it's the same idea. Yeah. Mm-hmm. No, so basically we make the BEC clouds sensitive to oscillating magnetic fields. And if we make different clouds, so let's say we have an array of them, of these atom clouds. If we make the different clouds sensitive to different frequencies of magnetic field, then we can essentially take a Fourier transform of the signal. And the signal we're looking at is the electrical spikes in the communication between neurons, so nerve cells. So that's very sparse in the time domain. So then if you take a Fourier transform, then that's kind of like asking the sweeping questions. So we're taking a partial Fourier transform of these spiky things. Yep.
So in Fourier transform, you expand your function in terms of harmonics. Try expanding in terms of different functions, say for example a wavelength transform, and how does that compare to what information you use?
Yeah, I mean, it's like in general it can be done definitely. Yeah, it's but it just happens to be, well, somewhat simpler to get our BEC to be sensitive to frequencies rather than wavelets or something. But you could definitely do it. But yeah, in general, it's just anything with, like, I guess, how would you call it? Like a Heisenberg uncertainty principle between two variables. I'm not quite sure of the exact terminology. And even actually, even sampling like a random signal basis, so basically measuring like dot producting against white noise is actually very effective, and is what the dense mathematical book it bases all its proofs from. Mm-hmm.
I'm wondering whether that technique can be used for recovering missing data in a data set.
Yeah, well, I mean, basically that's what I was doing here, right? So I deleted a bunch of data and tried to recover it, yeah. Yeah, so definitely, yeah. I'm not sure if it will be as effective as like a neural network or something, but yeah, definitely. Mm?
Comparing to neural networks, to that point, would you say like you've got X amount of compute and you want to do this recovery method that you've done?
Mm-hmm.
Saying I'm trying to do nighttime just with an RGB camera that has a really poor, like really bad dynamic range, so it has lots of artifacts. Would you say as a compute method, for example, this would actually be more efficient to do a very simple task?
Ooh.
Comparatively simple task. How quickly did you get that recovery out? I'm assuming it's not a very large image.
I think it's 512 by 512 by 3. How quickly? Tens of seconds, 100 iterations, yeah, something like that. I just used like the SciPy DCT function, whatever that is written in. I don't know. Yeah, I'm a Python person because I'm a scientist. So. Hmm?
What this is doing sounds like it's similar to like creating a wavelet. Using wavelets or representation. Is there some?
Yeah, I mean it's kind of just going between two different bases. So you could go like you could go from like a frequency basis to a wavelet basis or something like that. Or is it noise? Yeah, it might be noiselets to wavelets. I forget exactly, but yeah, it's yeah, as long as you have kind of a Heisenberg uncertainty relationship between the two bases, then you can do it. Yeah.
Awesome. Well, it is 7, so we should thank
Cool.
Alex.
Thanks for having me. All right.